Ice, ice, baby!
Hi, I'm Julia, a chemist by training. I'm the PI of the shape-dependent electrochemistry group, and I'm giving lectures on electrochemical impedance spectroscopy at Ruhr-University Bochum.
Hi, my name is Sebastian. I studied renewable energy systems at TU Dresden, and I'm an electrical engineer by training.
We research, for example, electrocatalysts for water splitting, and as you can see here, electrochemical impedance spectroscopy can be a very powerful tool for this, but it's not always easy to understand. With this video series, we hope to make it more accessible for our students and everyone who's interested in electrochemistry. Electrochemical experiments mostly follow the general principle to apply a perturbation to an electrochemical system and measure its response to learn something about the system's behavior. With system, I mean an electrochemical cell, where I can apply a potential to the working electrode using a potentiostat and measure the current response. For example, I can use chronoamperometry as a direct current method to discharge the electrochemical double layer of an interface to characterize it. We can also linearly vary the potential, such as in cyclic voltammetry, to investigate the redox potential of a redox couple in solution. The perturbation can be also an alternating potential, where we can use even different frequencies. The principle of perturbation and system response is the same in electrochemical impedance spectroscopy as in other electroanalytical methods. However, it is often much less intuitive for electrochemists than other approaches. One reason for this may be that it emphasizes analogies to electrical circuits to a high degree. Thus, we want to provide some refreshment for chemists in this regard. In this first video, we deal with current responses of ohmic resistors and capacitors and what impedance actually is.
Hello and welcome to our lab. First, I would like to show you how actual circuit elements look and how they behave if we apply a real step function with a potentiostat in a lab. You can see here two examples of such elements. The first is a resistor of resistance 1 ohm, and the second is a small capacitor with a 10 nanofarad capacitance. I will now connect first the resistor with our potentiostat to apply a voltage over this resistor. In this experiment, we will simply use the potentiostat to apply a voltage. We perform a chronoamperometry experiment with a step of 0.1 volts. You can see here the applied voltage. It is stable at roughly 0.1 volts between these two leads that you just saw me connect to the resistor. Now, experiment is complete. Let us look what the current is like. And you can see the current is pretty much exactly stable between 101 milliamps, actually 100.96 and 100.99. You can see slight deviations because in a real experiment the values are never quite precise and exact. But you can see the resistor is almost exactly 1 ohm. We have applied 100 millivolts and received a current of 100 milliamps. Easy enough. Let us now look at how the capacitor behaves. For this, we change the leads here and we connect it over the capacitor. See, it is now connected. And we apply exactly the same voltage as we applied before. And now let's have a brief look at the current that we can expect. The current that we receive is essentially a current peak when the experiment begins, and then a rapidly decaying current that approaches something like 0 here. In the real experiment, again, you always have noise, and you see this type of behavior. Okay, let's go back to the drawing board and have a look at how these responses should look like theoretically. Alright, let's get into the electrotechnical circuit elements behind the interpretation of electrochemical impedance spectroscopy. The most fundamental element that we're dealing with is the resistor, commonly symbolized by the capital letter R. this is the commonly used circuit symbol for this element. And we apply a voltage, commonly referred to with the capital letter U, and the index R in my case, so we can know that it belongs to the resistor. And through the resistor flows a current, which I will call here IR. Now, what is a resistor? Consider the case that you apply a potential difference, an electrical potential difference between 2 points, and between these points there is some real medium where charge carriers are present, and they can move in response to this applied difference in electron pressure. These arrows symbolize here the electrical field strength, capital E. This electrical field has the property that a charged particle within this electric field experiences a force. So in this case, a positively charged particle would be accelerated in the direction of the electrical field lines. Now, if the particle is accelerated, its velocity rises, and this process would obviously tend towards infinity. In a real material, there are other molecules, atoms, non-charged particles that obstruct this movement. At some point now, our charge carriers, whether they be positively or negatively charged, will accelerate and eventually hit these non-charged particles, transferring some of their energy to these non-charged particles. So the velocity that they reach does not tend to infinity in the mean. What this results in is basically that they accelerate only to an average velocity, which we assume to be proportional to the applied potential difference UR. And this is what we commonly refer to as Ohm's law. So, if we write this down as a formula, we have the current IR is equal to the applied potential difference UR divided by the resistance R. This resistance is basically the proportional factor, which describes what is the end velocity in the mean that these charge carriers reach, depending on the applied potential. What you should also notice is if a current flows through a resistor through this process, energy is dissipated. This resistor will heat up, and some energy in this case is transformed from electrical energy to heat. Consider now the second case that we will deal with here. What if we have a medium that really doesn't permit charge carriers to flow through? Whether there is no medium at all, whether we have a vacuum, or whether the medium is a dielectric, so basically absent any charge carriers, or free moving charge carriers. Then we are dealing with an electrostatic field, and the second element that we're dealing with, the capacitor, commonly symbolized with the capital letter C. And this usual circuit element and symbol. You can see this symbolizes the 2 plates of the idealized plate capacitor. So, again, we consider the case where we apply a voltage, again written as UC, and a current flows, in this case, through the capacitor, and I will deal with this in a second. Consider what happens now. Before, we had the charge carrier simply moving in accordance with the pressure gradient of electrons that we had applied externally. Now they can't do this quite so easily. Imagine now that we have the idealized plate capacitor. I will just draw it again here, larger. And we want to apply some difference in potential here. What do? We connect this externally and apply a difference in potential. Now, charge carriers will attempt to flow here, but then again they can't pass through this dielectric. Charge carriers will instead accumulate on these plates. And how you have to imagine the current flowing through the capacitor, it is obviously not flowing through the dielectric where no charges can pass through. What is instead happening is that, consider you apply a lower pressure of electrons, so a positive potential here, you withdraw some electrons here, and the electrons on the other side will move out of the conductor onto the plates. And what in essence results is a current that flows through the capacitor. But it is qualitatively different than the current that flows through the resistor. What we have here instead is an electrostatic field. And this capacitor is described by the characteristic equation of the capacitor. And this relates the capacitive current IC, C for capacitor, equals C, the capacitance, times the rate of change of the voltage or potential difference applied over the capacitor. And the current that is flowing here, you can imagine this as flowing, for example, here, and from these plates again here, all in the different direction. So, what we have here is different, because the current that flows is not proportional directly to the voltage that is applied, but to the rate of change of the voltage. And this brings with it important changes in the behavior, if we, for example, apply a potential step function, as we do in chronoamperametric experiments. Let us consider now the response to a potential step. First, for the rather simple case of the resistor. We apply a voltage, which I will graph here in blue, and I will plot it over the time schematically. And if we apply a step, then at time 0, we have 0 voltage, and at some time we commence the potential step. And we reach this kind of final voltage, and we turn on the voltage instantly. What happens now? This equation governs what the current response will be. And the current response is simply the voltage that we apply here, divided by R. So essentially multiplied with some proportional factor. So, the current response is shape-wise the same as the voltage. However, it is mediated in its amplitude by this proportional factor. Let us consider now the case of the capacitor C. Again, we attempt to apply a step function in potential to our system. So we put two poles from externally and connect these to this capacitor. Now, what is the current? This equation governs what the current will be. And the current is proportional to the rate of change of the applied potential. Now let's look at this quantity here. dUc over dt, the rate of change. In this area, it is 0. The voltage, the applied voltage, stays constant at 0 before we begin the experiment. In the end, when our step has been applied, it is again a constant voltage. This is 0. There will be no current flowing here in this region. However, at this moment, the rate of change in the step function is infinite. What this means is there has to be an infinite current flowing to apply these charges to the plates, because these charges are what establishes this potential drop. And another way to conceptualize this is the voltage that is in a capacitor in reality cannot jump. To apply a voltage over a capacitor means that you have to bring a different amount of charges on the plates of the capacitor. And these charges must be moved there for there to be a voltage over the capacitor in the electrostatic field. And this is the result of this kind of behavior. Alright, we just considered the response of our basic circuit elements to a voltage step. Now, as we have seen, the current in the capacitor is transient. So we have a very large current spike, theoretically infinite, but the stationary current response to such a voltage step is zero. And so if we want to probe similar systems and that have a similar response, then it might be convenient for us to use a voltage excitation that produces a current that actually persists and is not just transient. And for this, the most common excitation waveform is the alternating voltage, sometimes referred to as AC for alternating current, and it's basically a sinusoidal excitation. What I've plotted here is this excitation waveform. And what we're doing is a sinusoidal voltage. Now, for the resistor, we're familiar with this now. The current response of such a thing is again just proportional to the voltage. And no other shifts or any such modifications occur. It's basically just changed in amplitude and qualitatively the same. Now, as we can see, if we calculate the quotient of these two quantities, voltage and current, we will find that this turns out to be essentially the same value in all points where we calculate. So, if we divide here, this voltage value by the corresponding current, we will reach something just arbitrarily put here, for example. And we will find the same quantity here in all places, essentially, if we definitionally exclude the places where both quantities tend towards zero, where the function is not defined. So we exclude these points. Now, we can continue to describe this system with just one parameter. And this parameter we can again call R. And it is basically a proportionality factor that relates the current to the voltage. Now let us consider this case of excitation for the capacitor C. Now, the current that we can expect is described by this equation. And the current that we see is related to the rate of change of the voltage. And since we have chosen a sinusoidal excitation, so UC is some sinusoid with a given amplitude, then we can calculate the derivative of this. And if we take the derivative of a sinus, we end up with a cosine. And this is essentially just another sinusoidal function that is shifted by 90 degrees. And the way that you can visualize this easily for yourself, if you want to draw this, you take characteristic points to understand this properly. And you put yourself into the mood of seeing this through this equation. So IC is characterized by the rate of change of the voltage. So here, the voltage rate of change at this point is the highest, when it crosses the zero. Here, it changes the fastest, essentially, and this is where the current is the highest. In this case, it is the same, except the change is downwards. And in this place, where it peaks, the rate of change is 0. This is the turning point in the function. So, let us consider now what happens if we try to describe a system once more with just one parameter, by, for example, dividing voltage by the current. Consider this point. At t equals 0, where the voltage is 0, we have some positive finite current. And dividing those two results in a parameter value of 0. Let us again continue calling this parameter R for now. Now, let us look very close to where the current tends towards 0. What we have is the voltage near its maximum. But the current goes towards 0. At this point, before it reaches 0, it's still positive and increasingly small. What happens? We divide a very large quantity by an increasingly small quantity. So this quotient tends towards infinity. So it goes here. And of course, this point where I equals 0, this parameter is non-defined, because division by 0 has to be excluded. If we go here, past the point where the current goes through 0 and reaches negative values, we suddenly reach this function at minus infinity. And what we have is essentially sinus divided by cosine equals the tangents function. And this is not very useful in terms of parameter. So dividing these two gives a time-dependent value. And if we have a time-dependent description of this, then, well, that's of medium usefulness. So what can we do? We can help ourselves by realizing that these two waveforms are qualitatively similar. They are just shifted. Indeed, they are phase shifted by 90 degrees. So in this particular case, if we imagine the current shift by 90 degrees to the right, then the same calculation as on the left applies. This phase shift I will characterize here with the Greek letter phi. And this is basically the phase angle by which it is shifted. The sinusoid can be interpreted as running from 0 to 360 degrees, or 2 pi in this case. And here we shift it by 90 degrees, and we again obtain a description of the system where we now can form a time constant quotient of the two. And we can describe this current response fully, now not with one, but with two parameters. And this kind of description we are calling impedance. So impedance is essentially the description of the current response that we obtain when applying a voltage waveform that is alternating. So we have two parameters, R, which I will continue to call the resistance, but we must phase shift this for this to make any kind of sense. And so we have a second parameter, phi. And together they form the impedance. And the impedance is essentially the system description that mediates what kind of current response we get when we apply an alternating voltage waveform. And this interests us because this impedance is essentially characterized by our electrochemical system. The electrochemical system mediates what kind of current we get out if we apply a voltage waveform. And this is why we're interested in describing this in easy parameters here in this case. And the convenient forms and different ways to handle the impedance, calculate with it, and display it is something that we will handle in our next video. Thank you very much for listening.